Our next speaker is Professor Muriel Medard from MIT. The bio is posted on the web, and I guess she doesn't need any more introduction because, and also the floor is yours.
Thank you very much. Oh, sorry. Thank you, and thank you very much for the kind invitation. The presentation I'm going to give is very fortunate to have had the previous presentation before because Sarab's already set very beautifully the stage for the types of topics that I'm going to talk about, in particular the idea of having hybrid systems, not just because we're reduced to having hybrid systems, but because maybe we wish to have hybrid systems, and that's why I call it heterogeneity for keeps. Some of you may have heard me speak before. You know, I always say everything that's presented is a joint effort. I am fortunate to have a cadre of just amazing collaborators. I'd like to also always call out Ralph Koetter, who is my closest late friend. But any time I say something silly, I said that I came up with it all by myself. All right. So evolution. So we try to think of evolution as usually as, you know, there's one technology and then a better technology comes along and replaces the previous technology as some sort of linear evolution. We of course know it's not the case. I did 23andMe. I have Neanderthal. And one of the things that we realize is, of course, that the multiplicity of media is indicating that we don't have this kind of linear evolution, but if in anything, we actually are having a growing heterogeneity, and it's a heterogeneity that's probably here to stay and is here to grow. And the question is, does this heterogeneity means that we are dissatisfied, that people haven't come up with the right solution, or is it desirable, is it inevitable, and should we just embrace it? And if we're going to embrace it, how are we going to make use of it effectively? So how do we handle heterogeneity? So many of us here work at the physical layer or have to interact with the physical layer. We know what it means to have heterogeneity. It means that we have different noise characteristics, not just signal-to-noise ratio, but also variability, how the fading works because of different carrier frequencies. We have a lot of activity in this community about 5G and what happens at 60 gigahertz. It's not at all the same thing in terms of transmission as what happens at, say, 2.5 gigahertz. What are the different bandwidths? We just heard about slicing. Do you have a large contiguous bandwidth, or do you have a small contiguous bandwidth, small chunks of bandwidth? Much of the way our industry is going with things like sub-carrier multiplexing and OFDM is really splitting up the bandwidth into small slices. Some other technologies have been proposed in the past, like pulse position modulation, ultra-wideband, really require very large contiguous bandwidths. We're looking at different delays, particularly in terms of round-trip times. I'll talk about that in the context, particularly of satellite, which is probably the most extreme case of a long delay. Different congestion also. Different parts of the spectrum already have different things going on them, particularly traffic, which may already be existing. And we know what this means. As engineers, we know this means you're going to get different packet error rates. What you're worried about is the quality of experience, and if you're really worried about in-order packet delay delivery, then you really have to look closely at these things. So this tends to make us think that we really need to care about the physical layer. So we just heard about the advantages of virtualization. And for, again, many of us here who were sort of bred on the concept of doing physical layer, we really do think that, as an engineer, what's happening below everything is very important. But surprisingly, at least if you're thinking of it from the level of throughput, we just had a reference to capacity. Of course, we're closing on 2016, which is the 100th birthday of Shannon, the founder of information theory. What happens is that Shannon told us that you could have whatever. You could have a channel on the left that has errors, and you can make it into a channel that has no errors, all right? So interestingly enough, you can always go also in the reverse direction. Now, at first you may think, why on earth would you take something that has no errors? and stick it into a probabilistic model with errors. That's okay, I'll just wave, thank you, I'll use my organic pointer. But that's not exactly, you know, from point to point, that's not exactly very useful. But when you're thinking about a general channel, what this is really saying is I actually can separate network coding, the coding over the entire network, the use of the network, with what's happening locally, link by link. Now, of course, you know, there are exceptions if you have some multiple access, if you have some broadcast, but you know, the differences generally, unless you construct them carefully to really try to make a point, the differences are very small. So in effect, what this is saying is similarly to what happened with a separation theorem early on in information theory between source coding and channel coding, there really is a separation between channel coding and network coding. From a researcher's point of view, it's a bit of a disappointment. You know, if you spent much of your youth learning about physical layer codes, you feel like you should really be able to capitalize on that and bring network coding and channel coding together. But there is this separation. So really what this is saying is that, all right, separation and network coding, physical layer coding is something fundamental. So this is saying that in the same way that we don't have to worry when we transmit our pictures, how the pictures were generated, that we can do the compression of the pictures, for instance, separately from the transmission of the pictures, something we would have wanted to do from an engineering hygiene point of view anyway, because I can't imagine having to manage a system that has to keep track of whether I'm sending an email or a picture of my holidays or a movie, and trying to connect that to what's happening, for instance, in my 802.11 transceiver, and having that control to some extent, or at least determine partially what's going on in the modulation. In the same way that there is that separation, there is a fundamental information theoretic separation between channel coding and network coding. Okay? All work on network information theory notwithstanding. So this is giving a theoretical justification for virtualization. So at this point, I think it's very tempting to think that, you know, we can go ahead and just forget about all cross-layer. Again, you know, sometimes you do joint source and channel coding. It's because there's something specific like delay. So maybe sometimes there are very specific case studies where you may need cross-layer. That we should manage all errors at the physical layer, and we should just provide clean pipes to the network. So this would argue for a completely clean physical layer. Just clean it up at the physical layer, everything above is pipes. And indeed, that's very much the approach that much of industry and academia has taken. There's a problem, though. There's a problem with this because you have adaptation complexity and delay. If you're going to try to have the physical layer deal with all of your errors, all of them, the types of codes that you would have to conjure up would have to be so long and adapt to so many different things, not just the physical layer effects, but congestion effects at the higher layers, that it's very difficult to see how this would operate. So let me give you an example. I think this is running out of juice. Okay, so I'm going to talk about, I'm going to talk about random linear network coding. So I'm talking about algebraic random manipulation of packets that's happening at a higher layer. Thank you. And basically what this is saying is that if I take data rather than breaking into pieces, I'm just making modifications here. They're shown as a kind of quilt. Really, it's an algebraic mixture. They should all be brown. And really what this is doing is something very akin to MDS codes. Any mixtures are going to do. Okay, so let me see an abstraction here in terms of what's going on, say, in the physical layer. So I have a message. I split it up. It goes through randomly network coding. On the right, for those of you who are algebra jocks, I'm showing you basically the different representations, but you don't have to worry about them. I packetize it. That's basically the network layer. And then stop, physical layer, framing, MAC, everything else that's going on. Okay, so this makes a lot of sense from the point of view of, you know, the division between layering that we're used to, except that now see why we would want to have the coding at both layers, not just at the physical layer, but also at the next layer up. So how do we manage physical layer coding? Well, we see what the current situation of the channel is, and we adapt the physical layer coding to it. And usually you have just a handful of possible physical layer codes. You're not constantly, you don't have a continuum of them. So what happens is, suppose here on the abscissa, I have for binary symmetric channel crossover probability. From left is good, right is bad. And I'm using something very simple, Reed-Solomon, just for simplicity here. What we see is that the probability of error, as the binary symmetric channel gets worse and worse, before I go over and switch to a different code, things are getting worse. So if you look on the second line here, you can see that the probability of error is getting worse before I react and I switch to a different code, and then it goes down. So right before I've switched over, I am under-correcting. And by the way, right after I switched over, I am over-correcting. I'm never correcting just right, maybe just in the middle. Now what happens if I add some random network coding to it? What happens is that most of the time the rate is 1 because the physical layer is taking care of everything. And when the physical layer coding goes up, when the physical layer error code goes up, the network code rate goes down because I have to put in the redundancy at the network layer. So basically what happens now, if I look at the overall performance, what I have is that my overall good put, which is shown here in the bottom, my overall good put is nice and perfectly gracefully degrading with the probability of error as it should. Just to give you some idea of what this means for me to code in the next layer, this is some work done with my collaborators, Ulrich Spiegel and his group in New Zealand. These are experiments. They've been going on now for almost 2 years. This is Funafuti. I have never been there. I didn't know it existed. But it does, and it has very bad connection to satellite. And what you see here is the network coding effect. When you have the black dots are the packet losses. These are measured. The red lines are coding over with TCP, and the blue lines are the TCP such as it is installed right now. And what you can see here on the ovals there, the green ovals, is that you have several days where in effect you would have had no service on the island at all if you weren't coding. Because you really can't make up for everything at the physical layer, even in a very sophisticated system such as a satellite system. So this then asks the question, okay, I understand that I can separate the physical layer coding, but I don't want to do everything at the physical layer. I want to leave some of the coding to the network layer, because if I try to do everything at the physical layer, it's just not going to work. I'm going to end up in these kinds of situations no matter how clever I am. So does that mean that then I want every link to be just, again, a bit pipe, maybe with some things going on the network layer, but I still want to do everything on a link-by-link layer? Is that the right level, in effect, of virtualization? Well, let's think again about these types of things when we have dynamics. So suppose I have two systems going on, an LTE, a Wi-Fi, and I'm trying to do a hybrid system, and let's assume they have the same throughput. So I send the even ones on the Wi-Fi, the odd ones on the LTE. Okay, so I'm getting 1, 2, 3, 4, 5, 6, and then I reassemble them. The problem happens, say that the Wi-Fi goes flaky, then I get 1, 2, 3, 5, 7, 9. In order, delivery delay is bad. I can do all kinds of state tracking. I can figure out which packets I'm missing. How do I go and get them? By the time I got them, forget about the 5 millisecond delay we just heard about. It's gone. Never mind that. My throughput is dead. So if instead I code across these two, then what I'm going to have is that I'm going to have the right type of spreading between. And what's happening is, of course, every coded packet that I get is a useful packet. And by having every coded packet that I get be a useful packet, it means that in the system that I have here, I don't have to keep track of the different pieces. Maybe I have an uncoded area, but basically I'm just collecting packets in a way which really is enabling the full benefit of the coding. Just to give you an idea here, this is multipath TCP with RLNC. Multipath TCP such as it is currently understood in IETF. There's, of course, some modifications that are being done. And what you see here is the average throughput with uncoded, coded, and coded with a little bit more redundancy, and you can see the average rate, basically the abscissa there gives the log of the file size that you're downloading. And what you can see on the right is the emulation versus the mean field basically result of what you would have for the window. The reason I'm bringing this up is because it's interesting. You're not just opening the window and making some sort of rateless mess. Okay, you are having a sliding window. This is a well-behaved system. You're not just giving up everything in terms of your control. You still have a reasonable control, and you can see the window size there, particularly the blue window size when you add a little bit extra coding versus the black window size. But those window sizes are not sufficiently different really to account for the difference in throughput. And the reason this is interesting is because you see that this is probability of error, P there, that's shown on the right-hand corner, and RTTs that are very different. So here you have hybrid systems with different characteristics, and you're able to use them together. If you don't have the coding, which is the light blue there, your performance is very bad. Going back to what we had here as an example, when I was using the two systems and I was missing the packets that should have come to me from the Wi-Fi side, I wasn't getting the average of the two, I wasn't getting the sum of the two, I wasn't even getting the best of the two. Without the coding, I was actually getting the worst of the two. That's the worst kind of hybridization. And here you have very extreme differences between round-trip time. This would basically be geostationary on the right with very, very good physical layer coding. And on the left, this would be terrestrial with very poor channel conditions. Okay, so should the coding be done link by link? It's not going to be good to think of doing this link by link if somehow we can really think about this issue of dynamic behavior, dynamic delays, and really this decoding delay. So just to illustrate this again, the question of should I just be doing everything link by link? We know that we don't want to do things link by link when I have parallel links. We just gave a very simple example where that was happening because I had two paths, and if I didn't do the coding across the two paths, if I only coded, say, within a path, I wasn't going to get the sort of benefit that I saw. What happens when I have paths one after the other? So we're complicating the system. I have a multi-hop system. Well, suppose here I have a simple tandem of 3 links, and I do something, say, like a fountain code or some other rateless code where I code up front and I decode at the end. In this case, I need to put the cumulative losses in, so I'm going to have an overhead of 37% up front. If instead I recode without decoding, just keep recoding, because remember I had these random combinations. Random is great. You keep random all the time. You just recode even without ever having decoded. Then I'm going to get 10% losses on each link, which means a 90% effectiveness. So I only need, for that 90% efficiency, 11% up front, and I keep just adding it as I go along. Okay, just to give you some idea of what this looks like, if I look at this multipath with re-encoding, this is, I was very happy also going back to Saurabh's presentation that he mentioned SDN, because this is implemented with SDN. So you see those 2 links. You see the round-trip times. They have different round-trip times, different losses. The second link has losses that go from 0 to 10%, and that's down in the abscissa. So the loss probability there is varying from 0 to 10. And what you see on the ordinate is a throughput in terms of megabits per second. So the numbers here, you can see for coding with and without coding, or with TCP. Basically, you're stabilizing at the IP layer. We don't care about what's going on at the physical layer. The only effect of the physical layer is seen through the delay and through the losses. And what's going to happen here, what's interesting, is that I can recode at B, and what you can see is that by encoding only at A, I get a benefit, but by recoding at B, I get a very, very significant benefit. We're talking factors of 7 to 11, so really about a factor of 10, by doing things only only at an SDN and only at the IP layer. So again, bringing it all together, this idea of stabilizing, here I have another SDN example, very similar to one I had before, but now I have recoding and parallel paths. And you can see here the benefits that you get, even when you don't have as many losses, so your losses are only going around, you have multiple paths, so your overall throughput is better, you're still getting gains of about a factor of 5. So in effect, what we've done at this point is that, yes, there's a good reason to virtualize, coming from information theory. However, from an engineering point of view, you can't possibly do everything at the physical layer and only do the network coding, not worrying at all about the physical layer. But the interface between the two with erasures is actually a good interface. But if I'm going to have erasures in the network, I have to deal with them at the network layer. I cannot deal with them at the link-by-link layer. So errors, physical errors, go to the link-by-link layer. Errors that propagate up become erasures at the higher layer. And of course, other aspects such as congestion, drop down, and so on are also erasures at the higher layer. Okay, I just want to close with heterogeneity in storage. I mentioned it briefly at the beginning of the talk, and also it's in the description of my talk. If you look, in my opinion, at what's been going on in the network area and what's been going on in the storage area, you're seeing, I think, in the network area, a somewhat delayed version of what's happened in storage. So storage has always had heterogeneous systems. You know, the demise, for instance, of disk has been has been predicted for I don't know how long. It's still here with us because it's still cheap. On the other hand, when you look at solid state, the number of possible solid state technologies keeps growing. And one is not really replacing the other. Again, it's not this linear evolution. We're seeing them all come together at the same time. Storage has already become very virtualized. People understand in storage that it has to be virtualized. That has been facilitated to a large extent by the fact that if you look at what's going on in computer science, virtualization, first starting with virtual machines and now increasingly with container technology, Docker being maybe the prime example, has been occurring, and that has enabled a kind of virtualization very easily. When you think, for instance, of the multipath that I showed you before, I mean, in our area, it's still on the new side. If you think about what's going on in storage, people have been looking at multiple sources for a long time and coding across multiple sources. So that's already in there. The aspect that maybe really has not happened yet in storage is the idea not just of coding across multiple sources, multiple paths, but also of doing the continuous recoding that I showed you. Remember how I showed you with the examples with SDN of recoding in intermediate nodes? You can do the same thing. Can you please start it at the 20th second? Yeah. Thereabouts, it's fine, thank you. So here's an example. This is work with collaborators in Dresden, Aalborg, and Budapest. You have different nodes that have different chunks, coded chunks of data. And what you can see is that the red nodes are nodes that are dying, and the green nodes are nodes that are coming on. And instead of reconstituting all the initial data by connecting to enough other nodes to be able to decode and create a new coded version, they're only just recoding whatever they get. So they never get a full version. They're just on the fly recoding in a completely fluid fashion. And to give you some idea of what this does, this is a case where you see no coding, Reed-Solomon coding, and randomly linear network coding, where the three axes here are basically amount of traffic in the bottom right, amount of storage, and reliability being in effect probability that there is enough data in the network overall for you to be able to recover everything. Sorry, how much time do I have? 5 minutes? Okay. So when you look at this dynamic of robustness and repair, what you can see is that, obviously you need to code. having a structured code gets you some part of the way, but eventually dies. And the ability to be able to recode consistently and continuously, even without the ability ever to decode at intermediate nodes, is actually very powerful. Okay, so what does this lead us to then? What this leads us is to a fully integrated content delivery that is totally virtualized. And again, to reiterate, I'm coming from the physical layer. That's, where I got trained. So this virtualization is really coming not as something which, from the computer science going up. It's really, if you will, from electrical engineering coming up. No, not from computer science going down, but from electrical engineering coming up as just being justified over and over again by different aspects of information theory. Just as a side note, the thing that I just showed you, the analysis is very difficult. We don't understand fully the behavior yet, but I can tell you that it's not just a behavior because of averaging effects. So even if you have changes of the network that are adversarial, worst case Byzantine type of changes, that still holds. And there's some very interesting results in the theoretical computer science literature by people like Bernhard Hoppler at CMU and others that show this. So it's a very, very robust result. Okay, so basically what's going to happen here is data is just spread around the network, very much the kind of cloud concept that we saw before Barbara. And you add and you extract data on the fly. You add data as, you add redundancy if you have more losses, you squeeze out redundancy, you recode, and the entire network is completely fluid. And in particular, the integration of communications and networking is not an a posteriori integration that's done, if you will, almost reticently. It's an integration that it comes naturally because all you're ever doing is just handling data, whether it's on the fly or not. So it's really adaptive and mobile. To give you some idea of what this would look like, for instance, in a 5G network, we're talking about coded cloud storage, identify and manage resources, but everybody is recoding. So these sigmas that I'm showing there, these sigmas are basically doing linear combinations, linear algebra, and everybody's doing it. The intermediate caches are doing it. The storage and the cloud is doing it. The base stations, or maybe the node B is doing it. The phones are doing it. The phones are also communicating with each other just without having to decode, just by recoding. Everybody's recoding and sending on, and everybody's only adding as much redundancy and keeping as much data as is needed on the fly. And that's really the full vision in here. So basically, as I mentioned, we're dealing with information through the network in a fluid fashion. Manage errors locally. We do not want to propagate errors. Spread the variability across the network. And it's not desirable to separate the network coding at different links inside the network, even though it is desirable, as I mentioned, to separate the physical layer from the network coding, because we have dynamic behavior, we have different delays, we have different decoding issues at the receivers, and that needs to be taken into account. So the approach here, in effect, is to make a virtual network. And, as I mentioned, coming from the physical layer, an electrical engineer trained as an information theorist, it felt a little weird to sort of move away from physical layer coding. But really philosophically, and again, thinking back on this 100th anniversary of the birth of Shannon, philosophically is actually very close to what Shannon was doing. What Shannon did is he took symbols which individually were dirty, were not clean, were not able to be reliable, and he created synthetically, through algebra, he created synthetically a reliable link. And what we're doing is we're taking it to the next level up. We're taking a network which is a mess. You have different kinds of technologies at different places, operating in different ways, often with different protocols under them, okay? So I didn't go much into that, but we don't have here a sort of protocol homogeneity. There's no, I don't think there's a hope of making protocol homogeneity any more than there's a hope to make physical homogeneity in devices or transceivers. And basically what we're doing is we're just creating synthetically something that's reliable, an entire network, not just a link. We're opportunistic, we're omnivorous, and really integrating storage and networking. I think there's several issues I'd like to bring up in my last minute or so. First is who will do the integration? We just saw a very compelling argument from AT&T about they're doing the integration. I would say the AIC vision was basically this. Somebody's going to do it. And the question, I think, to some extent is it going to be the network providers or the network, maybe the network equipment providers also, who are doing the service for network providers? Or is it going to be, and this gets back to the same example as the Airbnb, is it just going to be a separate aggregator? Right? Am I just going to download an app that's going to manage everything for me, all my data, all my coding, and it's going to be completely virtualized, and they will be, in effect, making the money. And I think for us, even as academics, one of the reasons it's important is where should we put our energies? Should we be putting our energies more on a, let's say, more traditional structure, or should we already be looking to an aggregator structure? I think it depends on the choices the network providers make. Security. How do we manage our content? One of the things this allows us to think of is really managing our content in a coded fashion over untrusted, flaky networks and flaky storage. And finally, I just want to talk about the quality of experience. I didn't have much time to talk about this here, but I think one of the issues, again, as you saw in the throughput issue, that we could separate the network coding from the physical layer coding, but that there were issues with that as soon as we took into account dynamics. When we're looking at quality of experience, especially in the sort of very short delays that we heard about from Saurabh, the problem is that we're going to look not just at throughput, we're really going to have to look at the trade-off between throughput and delay. And that trade-off between throughput and in-order delivery delay is increasingly important as round-trip times increase, as the complexity of networks increases. Thank you.